Hello everyone, my name is Parinya Punpongsanon from University, and today I want to give a talk on behalf of my team on the paper called FoodFab, Creating Food Perception Illusions Using Food 3D Printing. And this work also together with Ying-Ju, Daisuke Iwai, Kosuke Sato, Marianna Obrist, and Stefanie Mueller. And the work in collaborations between Osaka University, University of Sussex, and MIT CSAIL. So eating too much is a real problem. So what we can do about this, we can looking for what actually causes us to feel either full or hungry. And we found that this is from the perceived satieties. The perceived satieties is considered as how the person satisfies with the appetites, rather than actual physical fullness. For example, one piece of cookie might be enough for sustain healthy. However, person might eat more to satisfy the appetites. And the way to reduce or balance the sustain healthy and satisfied appetites is eat slowly. To chew more food can enhance the perceived satieties. So how we can make you chew more? State-of-the-art technologies come up with the visually augmented the food by make it appears visually larger or change how it smells. Our method physically modify the food with the food 3D printing. Based on the 3D printing food with the difference in infill patterns and the infill density. We conduct the experiments to find out the best infill parameter, and so that people eat a lot of cookies in our study. Our experimental results found that the different infill patterns lead to different chewing time. For example, the honeycomb patterns make the participants chew more, comparing to linear, which make the participants chew less. And for more details, please looking for a paper. Based on the experimental results, we summarize that we might need to eat less honeycomb cookie than linear cookies to make you feel equally full. Let's come to details about this work. First, we need to address how these infill and chewing times are related to the perceived satiety. And let's look back to the previous work. Many researchers already investigated that the slower eating trend to reduce the amounts of food intake than the fast eater, due to the fast eating increasing the concentrations of the calorie in the blood, and that metabolism has turned from the calorie into the fatty acids. However, the chewing time doesn't only the ways that manipulate the food perceptions and eating longer or shorter. However, the size of the portions of food is reported as the effective ways to manipulate the food perceptions, especially to manipulate or to maintain the level of perceived satieties. Looking into the imaging field, researchers already translated this knowledge into the computational experience, for example, by using augmented realities. For example, by visually enhancing the size of food to manipulate the food intake. Or looking into how deliciousness of the food by manipulate or modify its appearance. While the previous work allows to manipulate the perceived satieties, the AR technologies are not practical as is need for physical attached to the body and modify the eating experience. In other words, we are seeking the ways to avoid this by doing it physically inside the food. And our solution is to use the food 3D printing to integrate it directly with the food so that it is no attachment necessary, and also physically enhance the perceived satieties based on each personal individual. So the next question is, what 3D printing parameters can we use to manipulate the chewing time? For a standard 3D printing machine, the typical parameters are the layer, infills, and the outer shell. The infills can be varies the mechanical properties of their objects, and so that we assume this could be applied to the food printing too. We're selecting most effective infill patterns, including the honeycomb, Hilbert, and linear, and the vary of the different infill density, including 70% infill, 50% infill, and 39% infill. The next question is, we have to understand how those parameters and the chewing time are related. To understand this, we conduct 2 user studies to find out the effective of the different infill patterns and the infill density to influence the chewing time. We selected cookies as the food choice for our experiments, as it's allowed to keep the study structure and the shape of the bake. In addition, we can directly compare our method to the state-of-the-art, like Narumi et al. In Kai 2012. In the first experiment, we compared three different infill patterns. The participants eat 10 cookies, each type per day. For example, they were asked to eat honeycomb cookies on the first day, and then they have to come back to eat the Hilbert cookie for the next day. During the experiments, we collect the chewing times through the EMG sensor, and after each cookie, the participant answer the questionnaire. And for more details, please refer to your paper. As I mentioned in the introductions, we found that the honeycomb infill patterns provide longer chewing time, while the linears provide a shorter chewing time. We fit the chewing results to the perceived satieties led by the participants and found that the perceived satieties is slightly increasing with the longer chewing time and slightly decreasing with the shorter chewing times. However, we cannot find the significant amounts of the different infill patterns. Not only the infill patterns, in the second experiment, we compared three different infill density by using the honeycomb infill patterns that provide longer chewing time from the previous experiment. However, for this time, we also modify the size of the cookie. For example, with the 29% of the infill cookie, it looks more larger, and 70% infill cookies will look more like smaller. Similar to the experiment 1, the participants eat 10 cookies each type per day. For example, they were asked to eat type 1 39% infill patterns in the day 1, and then come back for the type 2 55% infill for the day 2. From the experiments, we found that the cookie with the lower infill density but larger in the size provide longer chewing time, and the cookie with the higher infill density but smaller in size provides shorter chewing time. When looking at the questionnaire results, the participant laid the cookie with 39% infill but larger in the appearance, more full compared to 70% infills but smaller appearance. We found significant difference amounts of the three types of the cookie infill. To conclude, from the experience, we learned that 3D printed food with the different infill patterns and the infill density does affect to the chewing time. So the next question is, how can we integrate what we learned into the system that people use on a daily basis, so that we create a FoodFab system? The goal of our system is that users only input what they want to eat and how hungry they are, such that if they are not very hungry, the system will generate the shorter chewing time of the food for them. Otherwise, if they are super hungry, the system will generate the longer chewing time of the food for them. And to do so, our system consists of 3 steps. First, we build up this user interface that takes what user wants and how hungry they are. Then we compute how long people have to chew based on the chewing time required for infill. We develop a user interface that lets people input their hungriness, and the system calculates the printed food accordingly. This is how our system looks like. The debugging mode only appears for the demonstration purpose, and we can just ignore it by remove it out. User input the type of meal, such as breakfast, lunch, snack, or dinner. The system will usually calculate the allowable carry and the food printing parameter. The user also input how hungry they are in percentage from 0% to 100%. The system then calculates new printing parameter accordingly. Then user click generated food. The system prepares the food model accordingly to print the parameter, then directly send the printing model to the printer via the wireless network. Once the user input their preference, we then compute the chewing time based on the perceived satieties. We convert how the user is hungry into the perceived satieties so that we can manipulate the chewing time accordingly. The question is, how can we estimate the chewing time from the perceived satiety? So, in a previous experiment, we collected the relationship between chewing times and the increasing in the satieties by using the EMT sensor and the questionnaire results. We use that data to create the computational models that determine the relationship between the infill and the perceived satieties. Here, the result from the experiment 1 is to represent the shipping times and the perceived satieties for each participants per each type of the cookies. We fit the graph with the linear regression functions to estimate the change of the infill patterns to the perceived satieties, and this regression function is used as the computational model that calculates the effective food to satisfy the satieties. Okay, so now we are knowing how long people have to chill. So the next question is, what is infill should be used to print the food? So that we have to compute the infill based on the shipping time. Let's go back to the experiment 1. Our regression models not only indicate the type of infills to use for print the food, but also the area in which each infill patterns are effects to manipulate the perceived satiety. Together with the result from the second experiment, we can estimate the infill patterns from the user's satieties, then use the estimate shipping time as the input to estimate the infill density. And here is the food pipeline system. Please see your paper for more detail. And let's talk a little bit about the limitations. In our works, we only modify the proposed method with the cookie, and also to investigate the food 3D printing is only done with the two parameters, infill patterns and the infill density. However, there are a lot of more parameters to explore and other type of food to investigate, such as the 3D printing sushi, and so on. Also, we can use another fabrication method, such as to cut in strip of the bacons, or using the laser meltings or laser etching. And let me conclude my talk. The food perceptions and fabrications have a lot of opportunities, not only to tackle the food intake, but also to customize the taste structure of the food, improve the eating experience, or to change the ways of the food to be produced. And in our works, we only tackle the food intake issues through the modifications of the food internal structure using the food 3D printing, as the infill patterns and the infill density. However, there are more opportunities to this field that we would like to investigate in the future. For example, the food 3D printing should allow the persons to share the similar food experience from the different locations, or to support the personal food in the elder care homes. And this is all of my talk. Thank you for listening.